Okay, in this video we're going to take a look at the first of several reactions that our enols and enolates can undergo. And the types of reactions that we're going to look at are alpha halogenation. So this is where we install a halogen of some kind in the alpha position. So we're going to see how this reaction can be accomplished under both acidic and basic conditions. I think if our goal is to just add a single halogen in the alpha position, acidic conditions are most often the easiest way to go. And we'll see how it's different under the basic conditions later on in the video. But all I need to do is react my aldehyde or ketone with our halogen, Br2, Cl2, or I2. It doesn't work with fluorine, with an acid catalyst, and I can install this halogen, in this case a bromine, in the alpha position. Now let's take a look at the mechanism, and as we're going to see, because we have acidic conditions, that means the enol is going to be the reactive intermediate. In order to make the enolate, I'd have to have basic conditions. Okay, so this mechanism looks like a lot at first, but if we break it down into two steps, I think you'll see that the first half is a mechanism we've already done before. The first half is just the formation of the enol in acidic conditions, and we've already done that. So we have two proton transfer steps. First we protonate, then deprotonate when we're in acidic conditions. So first we protonate the ketone. We then have these two resonance structures where we can move the pi bond up to the oxygen, giving us the carbocation. And then in the deprotonation step, we remove the hydrogen from the alpha position and we form the double bond. Once we've formed the enol, we can then do the halogenation, which is really just two additional steps. So in the first step, the pi bond undergoes nucleophilic attack on the Br2. The lone pair goes on to make Br-. We form this intermediate. Now, I'll actually draw this differently later on in the video. Right, what we could have done is just done this mechanism in essentially the two steps to do the nucleophilic attack, and we could have left the single bond here, and then we could have shown the resonance structure where we had the single bond and the carbocation, and then showing the resonance structure for forming this second structure that's accomplished with this arrow. But the way that they've drawn it here is fine. I'll just draw it differently to see a slightly different example when we draw a mechanism at the end of the video. Then the second step of the halogenation is just a proton transfer, giving us the alpha halogenated ketone. Okay, so let's consider the regiochemistry of this reaction when we have an unsymmetrical ketone. So it turns out that the halogenation, the major product is going to occur where the halogen is added to the more substituted alpha carbon. So when we have this unsymmetrical ketone and we have two different alpha carbons, the halogen is preferentially going to be added to the more substituted carbon, and this will be our major product. When we add the bromine to the less substituted carbon will be our minor product. And we can justify this result if we consider the enol intermediate. And so if we consider these two possible enols that we could make from this ketone, this is the more stable alkene because it's more substituted, and so we'll have more of this enol formed than this one, and so this will give rise to this major product. One other note on the acid catalyzed alpha halogenation is that we can easily use a two-step synthesis along with this alpha halogenation to make alpha-beta unsaturated ketones. And so what I mean by alpha-beta unsaturation, if I look at this product, this is the alpha carbon and this is the beta carbon. And so we have a pi bond in between the alpha and beta carbons. And the reason this is important, earlier on this semester, when we looked at the Diels-Alder reaction, alpha-beta unsaturated ketones make really good dienophiles, and they're also going to be important in Michael additions, a reaction we'll look at later on in this chapter. And so the way the synthesis of this alpha-beta unsaturated ketone works is first we do the alpha halogenation, which would give us this product, and then if I hit this compound with a base, and so in this case pyridine actually works, we'll get an E2 reaction to give us the alpha-beta unsaturated ketone. And lots of other bases could be used for this elimination. The TBUOK that we've used a lot, or lithium carbonate. So a wide variety of bases can be used to accomplish this E2 reaction that aren't able to accomplish other E2 reactions. And for consistency, you'll typically see me use pyridine in this reaction. Okay, so alpha halogenation generally doesn't work with carboxylic acids and their derivatives, at least when we use a halogen in the presence of an acid catalyst. Now, it has been discovered that I can brominate the alpha carbon of a carboxylic acid if I react the carboxylic acid with bromine in the presence of PBr3. I'm not going to go through the mechanism. If you're interested, the textbook has a little bit more details. I think this is just maybe a useful reaction that you could add to your toolbox. Okay, thus far we've been looking at alpha halogenation under acidic conditions. We can also achieve alpha halogenation under basic conditions. So if I react this ketone with sodium hydroxide and bromine, I can also add a bromine to the alpha position. In this case, there are no hydrogens on this alpha carbon, so we can only add the halogen to this alpha carbon. Now, under acidic conditions, the enol is the reactive intermediate. Under basic conditions, it's the enolit that is the reactive intermediate. Now, this mechanism is a little bit simpler than the one under acidic conditions, or at least it's shorter. First, we're going to deprotonate our ketone to give us the enolit. And in this picture I stole from the book, they're not drawing it, but we could also show the resonance structure right, for this other form of the enolit, but probably the reason they didn't is because that's not the resonance structure that's going to be leading to our product. In the second step of the mechanism, the carb anion that was formed, the lone pair, undergoes nucleophilic attack on the Br2 to give us our final product. Now, one drawback of doing the alpha halogenation under basic conditions is it's very hard to stop at adding just one halogen. And usually polyhalogenation occurs. And to understand why that might happen, if you think about just forming the monobrominated product, in the course of the or once we've done the monobromination, we also have another hydrogen on here. And so if I deprotonate that with my base, that's going to give me a carb anion here. And that carb anion is going to be even more stabilized than the original carb anion, because now I have the halogen, and through inductive effects, it's going to stabilize that carb anion even more, making this proton even more acidic than the first one. And so it's going to be even more susceptible to the addition of another bromine. So if we want to add multiple bromines, that's great. If we just wanted to add a single halogen, then it's probably better to do this under acidic conditions. That being said, if we have a particular type of ketone, we can take advantage of this reaction to get a significantly different result. And so specifically, if we have a methyl ketone and we do the alpha halogenation under basic conditions, we can convert our methyl ketone into a carboxylic acid. And depending on the synthesis project you're doing in Orgo 2, this was maybe the first step in your synthesis, where you converted acetophenone into benzoic acid. And this is called a haloform reaction, because as we'll see in a second, the sort of byproduct of this reaction is either going to be chloroform or bromoform or iodoform, which is, right, bromoform would be that, chloroform would be that. Now, to finish up this reaction, if we just reacted this with sodium hydroxide and our halogen, we would end up with the carboxylate ion. To give us a carboxylic acid, we need to do an acid workup. So let's look at a little bit more about what's going on in this haloform reaction. All right, so I mentioned this in the last slide, but I want to mention it again because it's important. This only works with a methyl ketone. And so the way the rest of this haloform reaction would proceed is if we imagine we do the alpha halogenation under basic conditions, and I started with a methyl ketone. So originally this was just a methyl group. If I replace all 3 of the hydrogens with halogens, now this compound is susceptible to being converted into a carboxylic acid. And you don't have to worry too much about this mechanism, but I'll kind of go through it anyway. The first thing that we get is a nucleophilic attack with the OH from the sodium hydroxide. Right? We then move the pi electrons up to be lone pairs on the oxygen. And then, as we saw with the reactions of carboxylic acids, the reformation of the carbonyl group is a strong driving force. And so what happens is we reform the carbonyl group, and then the CBr3 leaves as a leaving group. Now, in that chapter on carboxylic acid derivatives, we usually said that carbon is a terrible leaving group, but there might be some exceptions we'll encounter later on. Well, this is one of those exceptions. So normally carbon is a terrible leaving group. The reason it happens in this case is because the presence of the 3 halogens stabilizes this methyl carb anion through inductive effects. And so while carbon is normally a bad leaving group, this is an exception because of the presence of the electronegative halogens. Now, when we're in basic conditions, you can think about it as either the base or the CBr3 that we made, and the CBr3 is probably the stronger base, so it's probably better to use it. It's going to deprotonate our carboxylic acid, and so that's going to give us the carboxylate ion, and then it also gives us, in this case, bromoform, which is where the reaction gets its name, the haloform reaction, right? We either form bromoform or chloroform, which would be CHCl3, or iodoform as one of our byproducts. And then this is also why we need the acid workup, because without the acid workup, we'd have the carboxylate ion. To get the carboxylic acid back, we need to add a source of protons. All right, so just kind of a summary on the haloform reaction. Under basic conditions, methyl ketones can be converted to carboxylic acids using excess halogen and hydroxide. We can do this with bromine, chlorine, or iodine. Fluorine doesn't work in these alpha halogenation reactions. And so this is a synthetically useful way to produce carboxylic acids from methyl ketones. And in the lab that many of you did, right, you converted acetophenone to benzoic acid. And this haloform reaction generally works best if the other alpha carbon doesn't have any alpha protons, right? And that was exactly the case when you had acetophenone. There are no alpha protons here, and so this was where the reaction was taking place. All right, so I want to finish up with 2 examples. I know this video has been long, but bear with me just a little bit longer. So first, I want to predict the major product and draw the mechanism for the following reaction. So I think it's easiest if we consider this in 2 steps. So first we have the alpha halogenation, and that's going to happen at the more substituted position. And so we're going to put a bromine onto the more substituted carbon. All right, and then our final product, when we then hit this with a base, we're going to get E2 elimination of this guy. And so our major product is going to be the alpha-beta unsaturated ketone. And so to finish this problem off, we want to draw the mechanism for the formation of this alpha-beta unsaturated ketone. And so first, we're going to want to show the mechanism for the formation of the alpha halogenation, and then the E2 step to give us the final product. So I'm going to break this down into kind of 3 steps, right? In order for the alpha halogenation to happen, when we looked at this mechanism before, we did it in 2 steps. First, we formed the enol. Then the enol underwent a nucleophilic attack to grab that bromine. Then we can finish it off with the 3rd step of the E2 reaction. All right, so the first thing we need to do is form the enol. So This is 2 steps, protonation and deprotonation. And I'm going to draw both resonance structures for my enol. And the hydrogen is going to be important, so I'll draw him in. All right, so then for the formation of our enol, the second step is deprotonation. So the water will come and grab that hydrogen. To give us our enol. And then in the next step of the alpha halogenation, my enol is going to do a nucleophilic attack on a Br2. And I think in the textbook, with the nucleophilic attack, they had a third arrow where we moved a lone pair down from the oxygen to reform the pi bond. And you're certainly welcome to do that if you want. I'm going to do it where I'm going to show both of the resonance structures. Now, my video won't let me slide down any further, so let me do it over here. So the resonance structure that I'm talking about would be this one. And so in the textbook, when they drew the mechanism, they included this third arrow in this step, and so they just showed the formation of this product. But I don't know, I kind of like better to show the resonance structures that we have, that we're forming here. But it is this resonance structure of the 2 that we're most interested in for finishing off this reaction. So to finish with the alpha halogenation, we're going to finish up with deprotonation of this guy. Okay, so that's the first 2 steps. So we formed the enol, then we did the alpha halogenation, and now the last step is the elimination. And so this is our pyridine, right? Basically a benzene where one of the carbons of the ring has been replaced with a nitrogen. And so this is going to be an E2 process. So the base is going to steal the hydrogen, the carbon-hydrogen bond becomes the pi bond, and then the bromine is going to take off as a leaving group. And so that'll give us our final product. I'm sorry things got cramped down here at the end. My video software wouldn't let me scroll down any further, so this was all the room that I had to work with. All right, so we've predicted our major product, and then we've drawn the mechanism to form that. I know that this mechanism seems pretty long, but if you just want to break it down into steps, first form the enol. We know how to do that from previous examples. Then form the alpha halogenated product. And then finally, the last step is an E2 reaction that's just back from chapter 7. Okay, one last example, and this is a synthesis example. So we want to identify the reagents that I could use to transform this starting material into this final product. And so when I'm comparing my starting material to my final product, what I'm kind of noticing is, right, this is all the same, right? And so all the action is happening here. And I formed an ester from this compound, and I think specifically because in this chapter we've just talked about the haloform reaction, right? If I could turn this into a carboxylic acid, I could use Fischer esterification to convert that into an ester, so that's pretty easy. So how can I convert this into a carboxylic acid? Well, if this was a ketone, I could use the haloform reaction to convert my methyl ketone into a carboxylic acid. So then the question really is, is there an easy way to turn this into a ketone? And we do have a way to do that. If we go back to chapter 8, ozonolysis is a way to chop off a carbon-carbon double bond and install an oxygen on each of the carbons that had been part of my alkene. And so I don't care about what happens to this, but if I chop it here and put an oxygen on using ozonolysis, yikes, that's DMS. Sorry for my terrible writing there. But that's going to give me the ketone that I wanted. And so now we have a methyl ketone, so we can use the haloform reaction that we learned. And that will convert my methyl ketone into a carboxylic acid. And then the last step from last chapter, if I do a Fischer esterification, and I want to add 2 carbons, so the alcohol I want is ethanol. And that is how I can accomplish this synthesis.